I think I left you guys here where we started with the symmetry adapted linear combinations, right? So I'm not going to repeat the whole part, but this part, the linear combination of atomic orbitals, I hope you have looked at the earlier video. There what we said is that we take the linear combinations of the atomic orbitals, like we took hydrogen molecule, and then we showed that if we take one is A, one is B, sitting on the two center, then we take the plus minus combination, right? So sigma is going to be plus combination and sigma star going to be a minus combination. So that is the normal way we do it without the symmetry consideration, right? Now, if we go for the symmetry adapted linear combination, we have a couple of things to do it. So that is basically how we consider the symmetry of the orbitals, and then what is the way we combine them, right? Okay, so here we go. For constructing molecular orbitals, we will do it like exactly in this similar way what we did for the vibrational analysis. So first thing is that whenever we want to construct the molecular orbitals, what is going to be the choice of bases, right? So now, as we know, the molecular orbitals are coming from the atomic orbitals. So the natural choice is going to be orthonormal functions of the atoms which are in the molecules, right? So those are basically set of functions which are atomic orbitals, and they are of course orthonormal when they're sitting in the two other atoms, right? Now what we do then, we take the linear combinations of those atomic orbitals in such a way that the resultant combinations form the basis for the irreducible representation of the same molecular point group, right? And so that means the representations, like let's say if we take the water molecule, then C2V, so I'm having 4 irreducible representations, right? So then like C2V, if we go for, then I am having A1, then A2, right? Then B1 and B2. Okay, so idea is that now if we take the atomic orbital of like oxygen atoms and hydrogen atoms, we should take the linear combination in such a way that the resultant combinations should be following these irreducible representation. So that is the one thing we have to remember, that is the combination form the basis for irreducible representation. And second thing is that those combinations are going to be orthonormal, because any function, if it is going to be any function, set of functions are going to be acceptable if they are going to be orthonormal, right? So these are the things we have to remember, right? So now I remove this. Okay, so now what exactly we call is the SALC. Now, question is that if we combine them, these combinations which are based on symmetry, right, they are called basically symmetry adapted linear combinations. So those are basically linear combination of atomic orbitals, but it's based on symmetry, right? So therefore, we call these symmetry adapted linear combinations. Of course, they are coming from the atomic orbitals. So therefore, actually we call them SALC. AO. So this is coming from the atomic orbitals. Right. Now, this is also this we discussed in the previous session also. Now, how really we do it? Right. To do this, we need to take help of some projection operator. So that is basically the way it does is how we combine those atomic functions on individual atoms in a molecule. So what is the way to combine them, or what is going to be their proportion, how they are going to combine, right? So now projection operator is, if we say in a other way, like if we take a molecular orbital, which is the resultant, now when we project that MO onto the corresponding atomic bases, right? So let me just do it like this. I think if you have looked at, so let's say these are the two bases. Like let's consider I am going for the H2 molecule, and I am having sigma and sigma star, right? Two orbitals. Now this is going to be plus combination, and this is going to be minus combination of two 1s orbital. And by now you know this is going to be square root of 2 this, and then 1s A plus 1s B. I hope you understand what I am talking about. So this is small 1s A, 1s B, and then this is going to be the minus combination. I'm not going to write this. Now, if I take this is the basis in this scale, there is 1s A atomic basis, and this is 1s B. Now, sigma, we can think about like a arbitrary vector. So let's say this is my sigma. Right? Now, if I think about what does projection operator does, is basically it's like I'm comparing with the classical analog. It's not exactly, but it's not the way we do the projection on the x-axis and y-axis. So if we project it on this, then this part is going to be 1 by square root of 2, which is this one, right? Now, if I project that also, right, my drawing is not exactly proportion, but it has to be like that. But anyway, so this part is going to be also is going to be 1 by square root of 2, right? So that is basically the projection, what we are projection operator we talk about. So so the first line, what we say, this is the proper way to combine atomic function in an individual atom. So if we proper way means what is going to be the coefficient. So that can be done using the projection operator, right? So I did it here in the reverse direction. So that means if we know the MO, so that is sigma, if we project it on the atomic basis, then what is going to be the coefficient, right? So that is basically the comparison with your Cartesian coordinate system. Like if we take x and y, so that is the way normally we do it. Okay, so now this of course is having a different relation. So let me bring the relation here, how we do it. So that is the kind of relation of what we are going to use this. So this is actually the MO we are going to form. So let me tell you, like this I stands for the irreducible representation. So this is MO of type ith irreducible representation, which can be generated like this. This phi is atomic orbitals, right? So this is going to be one of the atomic orbitals, and pi is the projection operator corresponding to the symmetry I. So that means if I take water molecule, this I can be A1, A2, B1, and B2, right? So projection operator actually pi goes like this. So atomic function is here. Now projection operator does like this. So first we need to perform all the operations on the wave function, atomic function. Then we need to multiply the character of the irreducible representation of ith irreducible representation, right? So if I go for water molecule and if I take A1, so then these characters is going to all are going to be 1 for individual operation. Then if you sum them up over all the operations, that is going to give you the resultant molecular orbitals of symmetry type is going to be, let's say, A1, right? If I go for character A1, then it's going to be A1. If I go for like B1, then it's going to be molecular orbital of B1 type. Okay, so unless we do it, it may not be that clear. So let's go for the system what we are sticking to this class. So first one we will go for the water molecule, right? Because we are having C2V and C3V. So first I'll be going for water molecule which is C2V, and then I'll go for C3V. So now initially you have to think about this water molecule. First thing is that we need to know the point group, right? So we know that this is going to be C2V, right? Okay. Now, what do we have to do it? Like the way I do is like we separate it out. The central atom, like here central atom is oxygen, and we kind of call it ligand atom, so that which are connected to the central atom, right? So we separate like this. So this part I'll be taking as the ligand groups, right? So I'm just writing L, and oxygen is going to be the central atom, right? So we'll initially we'll combine the atomic orbitals of these two hydrogen atoms, and then we'll combine this with the atomic orbitals of oxygen, which is the central atom, right? Okay. So next step, so you go stepwise, is construction of SALC. Now here SALC means I'm going to do with this atomic orbitals of two hydrogen atoms. So this is going to be 1s-A and 1s-B. So what is going to be the choice of basis? The choice of basis is natural choice is going to be the 1s-A and 1s-B. So A is sitting the atom A, and 1 is B, basically B is sitting on the atom B, right? Now, so this is the choice of basis. Now we have to generate what is going to be the reducible representation based on this basis, right? So generation of corresponding reducible representation, right? So if we take this basis, one is A, one is B, now what should be the reducible representation, right? That's what we are going to do it here. Okay, now we can do it in like using a matrix representation, what we learned earlier also. Like we apply the different operation on the on this basis, and then try to fill up this characters from this, right? So like if I take operation R, right, then operating on this basis, which I write like 1 is A and 1 is B, right? And then it is going to give the my resultant basis, whatever it is, depending on the R, right? Now, and based on that, I'm going to have the character for the operation, right? Now, when R is E, let's say identity. So identity when operates on this basis set, then what happens? Now this basis remains same, right? So that means 1 is A remains 1 is A, and 1 is B remains 1 is B. So the corresponding matrix for identity, I think you can do it easily. That is going to be 1s, 0, and 0, 1, right? So therefore, the character for this identity is going to be 1 plus 1, so that is going to be 2. So I write 2 here. Right. Now, if I go for C2, then what is going to be the matrix? So if R is going to be my C2, then what is going to be the matrix? Now look at here, if I perform C2 along this Z axis, 1 is A becomes 1 is B. Now 1 is B becomes 1 is A, right? So that means if I operate on the basis 1 is A and 1 is B, then what has to be my matrix to get the resultant? Look at here, 1 is A becomes 1 is B, right? So that means this should be 0 and this should be 1, right? Then only I can get like 1 is A is going to transform to 1 is B, resultant one, right? Similarly, 1 is B is going to transform into 1 is A. So therefore, I am going to have 1 here and then 0 there, right? So the matrix what we are going to get is basically this one. So I remove this now. Right. So that means C2, if the operation is C2, the corresponding matrix representation is going to be 0 1 1 0, right? So the character corresponding to this C2 operation then must be 0. So 0 plus 0, that is going to be 0, right? So therefore this is going to be 0. Okay. Now exactly in the same notion, if I go for sigma v, so sigma v is going to be again sigma v xz, right? So xz plane is this one, right? So if I go for this, so then again 1 is A goes to 1 is B, 1 is B comes to 1 is A. So the matrix is going to be similar for sigma also, sigma V X Z also, right? So therefore this is going to be 0 again. Now sigma V prime, which is YZ plane, so that means this is the plane of the screen of the computer. So that means both 1 is A and 1 is B remains unchanged, right? So individually they remains unchanged. So therefore each contributes 1, so that matrix representation will be going exactly same as your identity, right? So therefore this is going to be 2. Okay. So now that we got reducible representation based on these basis, right? One is A, one is B. Now, if I reduce this, I should be getting what the irreducible representation, and that has to be 2-dimensional because its identity is having 2. So any two of the irreducible representations of C2B point group are going to combine and they're going to give this, right? So for that we need to reduce this using the reduction formula, whatever we learned earlier. That is basically how many A1 is going to be there, how many B1 like this. So I'm not going to do it, but instead what you can realize is that in looking at the character table, like which of the two irreducible representation, if I combine, then which of the two are going to give this result, right? So you just try to work it out. I'm just writing up here. So that is going to be E1 plus B2. Okay, so what does that mean? This means that if I take the atomic orbital basis of one is A, one is B, and I want to form their linear combinations, I'll be getting two SALCs, right? Because they are going to be symmetry adapted. One of them are going to be A1, and one of them is going to be B2, right? So how this combinations are going to be looking like? So for that we need to go for the projection operator, right? So let's do the projection operator, how this projection operator is going to look like. Now here if you can see that I'm going to go for the SALC of A1 symmetry, right? Because like using these bases, what I realized that I'm going to have two types of SALC. One of them is going to be A1, another is going to be B2. So now what is going to be the shape, or what is going to be the structure of E1 SALC? So that can be done using the projection operator, which I just hand waving way I've discussed earlier. But now we exactly will use this formula and try to do it how it can be done, right? Okay, now we go stepwise. First we take this is the basis and then do the operation, right? So if in this table I'm going to fill it up slowly how it is going to be, right? So now if we go for operation identity on 1s A, this remains 1s A, right? Now if we do C2, look at here, C2 along Z, so this 1s A goes to 1s B, right? So after performing operation, so I go at 1s B, right? Then exactly in the same way, if I do sigma VXZ, 1s A goes to 1s B, so that is going to be 1s B, and then this is going to be YZ plane, so 1s A remains 1s A. Right. Now, what is the character of A1? All of us, we know that this is going to be 1, this is also going to be 1, this is 1, and this is 1. Right. Now, if I do the next step, then I multiply these vertical lines. So then we will be getting, so we are going to multiply. Right. So all of them remain the same because it's multiplication with 1. So this is 1s A, this is 1s B, this is again 1s B, this is 1s A, right? And the last step is going to be now the sum over all the R. So sum over all the R means what I have to do, I have to sum them up. So if I sum them up, what do I get? I get this SLC of A1 type, right? So that is psi 1A is going to be equal to, if I sum them up, I'm going to get 2 1s A plus 1s B, right? Now that you have to realize that this is not normalized. So we have to normalize this because normalized functions are going to be only acceptable, right? So normalization procedure exactly the way we have done earlier, like something like this: psi star psi d tau. This has to be 1. So if you follow this procedure, you should be able to get what is going to be the value of the normalization constant. Now, if you do this, it's very easy to do it. Try to do it, and you will realize is that this normalization constant is going to be something like 1 by square root of 2. Right. So this normalization constant is going to be 1 by square root of 2. So therefore, I say that my SALC of A1 type is going to be 1 by square root of 2. 1 is A plus 1 is B. Right. Okay. Now, what about the I have one more type SALC, that is B2 type. So that is going to be something like this. Again, we follow the exactly same way, and we sum them up, right? So if you do it quickly, so that is going to be something like, this is 1s A, right? Exactly the earlier slide what we did. This is going to be 1s B. This is again 1s B. and this is going to be again 1s-A. Right. Now character for this is going to be 1 minus 1 minus 1, and this is 1 because this is B2. So that is going to be minus 1, and this is going to be minus 1. So if we do that, that is going to be 1s-A, right? And this is going to be minus 1s-B. This is going to be minus 1s-B, and this is going to be 1s-A. Right, now if we sum them up, what we get? We get actually the psi, which is SALC of B2 type symmetry is going to be 2 1s-A minus 1s-B. Right? Again, if we normalize this, after doing the normalization, then what we get is something like 1 by square root of 2. Right? So these are the two SALCs. One is A. SALC is the earlier slide what I showed is going to be A1 type, which is going to be the plus combination. Now this is going to be B2 type. It's going to be minus combination. Right. So these are the two SALCs. What we get on the basis of this. Now these two SALCs are going to be combined this central atom according to the symmetry. Right. So if we want to do that, so we need to know the symmetry of the atomic orbitals of oxygen atoms also. So